Right. Um, it's my great pleasure to introduce today's speaker, Nina Miolane. Is that how you pronounce?
Yeah.
Um, Nina is an assistant professor at the Electrical Engineering and Computer Engineering Department at UCSB. Her research group, BioShape, aims to create computational representations of the human body at different scales. And today we'll talk to us about Geomstats library for differential geometry.
Thank you. Thank you very much for the introduction and the invitation. I'm very happy to be presenting our research today. So I will talk about the software Geomstats, which is a Python package for geometry and statistics and machine learning. And what that means is that it is an implementation in Python of manifolds that are curved data spaces and mathematical structures that can equip these manifolds so that the statistical learning algorithms that follow are aware of the geometry of these manifolds. And that is in order to ensure that the statistical learning algorithm have an improved interpretability and possibly an improved accuracy. Most importantly, today, I will present the mathematics that exist behind the design of the architecture of Geomstats, behind the design of the architecture of differential geometry. Now, talking about the architecture of mathematics is not new. It was actually already mentioned by Bourbaki in the 1930s. Nicolas Bourbaki was the pseudonym given to a group of French anonymous mathematicians whose original goal was to prepare a textbook in analysis. But over time, their project became much more ambitious, and the Bourbaki collective ended up reorganizing the whole field of mathematics, and even in passing, renamed it Mathématiques, singular. So this is the architecture of mathematics in the 1930s. And even though many things have changed in mathematics since then, I think that the way of phrasing mathematics as being architectured resonates a lot with today's era. And this is because today, and since the 90s, we have started to talk about software architecture. Now, mathematics can be thought of being built from axioms, so as to prove whether logical statements are true or false. And in a similar way, software can be built from elementary components so as to achieve certain tasks. So we already see a parallel between mathematics and software. And since both mathematics and software have been built or architectured by humans, we can start to wonder whether there are some design patterns that are shared across mathematics and software. And so maybe we can use concepts from software architecture to effectively implement the architecture of mathematics. And today we're going to see that this can be done. And my goal is to show you an implementation of the architecture of differential geometry. But beside the academic interest, you may ask why we would want to do this. So how can an implementation of the architecture of differential geometry be useful? A first idea will be to use this implementation of differential geometry to ask mathematical questions. So you could use an implementation of that field of mathematics to get intuition on proofs. I'm not going to focus on that today. And by the way, getting intuition on mathematics is something that you cannot really do with modern AI, such as ChatGPT or models like that, because you can ask them differential geometry questions, but they might not give you a truthful answer. But anyway, we won't focus on that. Today, I'm going to show why we could be interested in implementing architecture of geometries in the context of doing ML, that is machine learning, on a data space that has some geometric structure. I'm going to explain what geometric structure means for a data space. So this is because statistics, machine learning, and deep learning have known incredible successes across numerous fields of science and industry but most of the theory has been developed for spaces such as the one you see on the screen. So most of statistic machine learning and deep learning has been developed for data that belong to a flat space or Euclidean space. You see 4 data points on the Euclidean space here. But however, many data sources that we encounter in practical applications have more structures than that. So the data space can be curved. First example of data space with structure would be the sphere or the Earth. So any event happening on the surface of the Earth, such as earthquakes, are actually data points on a curved space that we call a manifold. So that's the first type of structure that can equip a data space, is the structure of curvature. And such structure of curvature happens every time we have data that have nonlinear constraints. So for example, an event on the surface of the Earth is restricted to be on the surface of the sphere, and that is a nonlinear constraint. So that's the first type of geometric structure that can equip the data space, curvature. Another type of geometric structure that can equip a data space is the notion of equivariance of invariance, which is a type of properties that arise when we use transformations to act on data points. So for example, assume you have a few data points on the surface of the Earth, and you operate a transformation such as a change of coordinate system. Here I've just rotated the coordinate system. You would want to enforce that any machine learning algorithm that is performed on these data points before the coordinate system is changed will give the same result as it is performed after the coordinate system is changed. The results of the data that you're extracting from these data points should not depend on the coordinate system chosen. So that's a property of invariance. And more generally, any type of data that has that type of property is data with symmetries. So symmetry is the second type of geometric structure that we can equip a data space with. And even if we do not know a priori what type of geometric structure exists on our data space, we don't know if it's curved, we don't know if it has some symmetric properties, we can call on the manifold hypothesis, which says that generally data in a high dimensional space has to form a lower dimensional manifold, such as the Swiss roll that we see here. And even if we don't know what is the structure of the data space a priori, we can discover that structure with methods such as manifold learning or even symmetry learning, so that after that manifold learning step, we know that our data is on a manifold or a curved space.
Does the manifold hypothesis say that it's probably also on a smooth manifold?
Doesn't matter if it's a smooth manifold for the way we implement differential geometry. Yes, not necessarily smooth, but at least several times differentiable. It depends on which type of tensors you are looking at. So for example, if the manifold is smooth or it's second order differentiable, that you can have tensors of curvatures, because tensors of curvature requires the second derivative of the function defining your manifolds. And I think there are other tensors that will require higher order derivatives. And so, yeah, it's better if it is smooth.
Okay, thanks.
Thank you. Good question. So data spaces have geometric structure, whether we know it a priori or whether we discover it with, let's say, a manifold learning step. Now we want to implement the architectures of differential geometry so that we have machine learning on data spaces that respect this geometry. And so you may wonder, why would we want an algorithm, machine learning or deep learning algorithm, to be aware of the geometric structure of the data? And even if it is aware of it, why should it respect it? And what does that even mean? So a first argument is that if your learning algorithm respects the geometry of the data, it uses what we call an intrinsic representation of the data, which means it uses as few as possible degrees of freedom to represent the data. And that means less computationally expensive and also more interpretable results. So taking the example of the sphere again, assume you have an event that is happening on the surface of the sphere, which is recorded by X, Y, Z coordinates in green on the left side of the illustration. Well, it is easier to speak about an event on the surface of the Earth using a longitude and latitude coordinate. Not only it's only two coordinates to keep track of, latitude and longitude instead of X, Y, Z, but it's also more interpretable. So that's what we mean by respect the geometry, using as few degrees of freedom as necessary to represent the system. You have fewer parameters, better memory requirements, and also it's going to become more interpretable. And the second argument in favor of respecting the geometry is that we use that as a geometric prior, or you could call that an inductive bias. We are injecting mathematical knowledge in the machine learning algorithm, and that can lead to more robust, more compact, and more generalizable learning. For example, assume you have the epicenter of an earthquake propagating on the surface of the Earth, and these are the pink dots that you see on the green Earth. And you want to understand where the earthquake's epicenter is gonna propagate next. If you didn't respect the geometry of the data space, you could ignore completely that the earthquake has to be on the surface of the Earth. And in that case, if you have a restricted budget, you might be able to use only the simplest model of machine learning, which will be linear regression. And so you will draw this yellow line through the data that represent the epicenters of the earthquake and maybe predict the next epicenter to move in a location that's not even on the surface of the Earth. Whereas with the same budget of parameters, you could do geodesic regression instead, which is what you see on the right of this illustration on the green Earth. And then you would predict the next epicenter that is at least on the surface of the sphere. And so by adding this geometric prior, this mathematical information, you can have more compact and more generalizable learning. So this was to motivate that it's interesting to have an implementation of the architecture of differential geometry to build machine learning and deep learning algorithms that respect the structure of the data. Now, there have been some Python packages that are linked to differential geometry and statistics, machine learning and deep learning, but they either focus on optimization and differential geometry, so optimizing a cost where the parameter belongs to a manifold, or they focus on a very specific type of manifolds or data space. For example, on the table, you can see we have pi-quaternion. That is a Python package of machine learning dedicated to one type of data space. The data space is the space of 3D rotation. And pi-quaternion is awesome to compute with rotations, but it doesn't abstract this idea of computing on data spaces while respecting the geometric structure. So we could say that we are missing a general numerical implementation of differential geometry that in addition will be well unit tested so as to be useful for a wider community. And so that's what we try to address with this open source project that's called Geomstats, or Geometry and Statistics. And our goal is to code differential geometry for learning, that is statistical learning, machine learning, and deep learning. And so in this talk, I'm going to talk about the coding part, the geometric part, and the learning part. Starting with the coding part. So I'm going to introduce what is the user's perspective on Geomstats. So let's say you want to build a machine learning algorithm that respects the geometry of your data. What are the few lines of code you need to actually do that? And then I'm going to present the coder perspective, which is how everything is implemented behind the scene in order for the users to call a statistical learning algorithm on their data that live on this data space with more structure. And the concept we use are concepts from object-oriented programming. Okay, but starting with a user perspective. Let's say you have some data and they belong to a curved space. Let's assume for now you know to what manifold or curved space your data belong. So you have a few data points, for example, on the surface of the sphere. Maybe it's another curved space for you, but let's imagine it's the sphere. And you want to run a statistical learning algorithm that respects the geometry of your manifold. And for the sake of this introduction, let's say the statistical learning algorithm that we want to run is just computing the mean. Even in this simple example, we can get the user perspective on using Geomstats. So first, we run 2 lines of codes which aim to tell the software which type of data space we are working with. So here we're working on a sphere, so we need to instantiate a data space that is the sphere. And we do that by importing a class, a Python class that's called hypersphere. And we instantiate our data space, which is a hypersphere of dimension 2, because it's the simple sphere. So first we create an object that represents the data space that we are working with. And second, we run the statistical algorithm that we have chosen. So in that case, it's just the. And maybe what's different compared to scikit-learn, if you work with scikit-learn, is that the statistical learning algorithm takes as input the manifold, that is the data space that we just created. So in this second step, you can imagine that instead of giving it the manifold that is the sphere, in the general case, you can give it whichever manifold that you have instantiated in the first step. So we're adding this new parameter to any scikit-learn type machine learning algorithm. This new parameter is a manifold that knows its own mathematical structure, such that the statistical learning algorithm that follows is going to respect the structure as much as possible. For the first step, we used a sphere, but I want to mention that you can use other type of geometry. And in particular, even if you do not know the geometry of your data space, you can learn it and then input the result of your manifold learning algorithm in this first step. Okay, but that's the user's perspective. Let me move to the coder perspective and what is happening in particular behind the scene when the user writes these few lines. I'm going to introduce patterns, design patterns of object-oriented programming to show you what type of mathematical structure we can create. Okay, so here, when the users write this line, we are instantiating an object, Python object called sphere, that is of the class hypersphere. And in the next slide, I'm gonna use this type of box to talk about Python classes, where the name of the class will be in red. The first line of the box will refer to attributes of the class that are variables that are associated with the class. For example, dim stands for dimension, and it's an attribute of an hypersphere. Dimension equal to creates a sphere. And the second line of the box will be the methods, meaning functions that are associated with a Python class. And it's basically the things that the hypersphere knows how to do. So for example, an example of method can be belongs. You can give a point to the hypersphere and the hypersphere can tell you whether that point belongs to it. So that's the overall design. Class name, attribute, and method. It's the foundations of object-oriented programming. And now we can use a concept, another concept from object-oriented programming, which is the concept of inheritance. And that's going to be very useful for the coder to encode mathematical abstractions, because we're going to be able to build a hierarchy of data spaces from the more abstract to the less abstract. So in the less abstract column, you can see the hypersphere. It's a quite concrete example of manifold. But we can build more abstract manifold. For example, we can build a manifold that is a bit more abstract, and that's called level set. A level set is a manifold that can be thought of as being a set of points that have the same level, so that take the same value under the application of a function. So for example, if the function is x, so x is a point, x squared minus 1, that's the function. I can think of the sphere being a level set because it's the set of all points x such that the function x squared minus 1 has the level 0. So that's a more abstract manifold, of which the hypersphere is only a more special case. So we would say in that case that the sphere is a child class of the parent class level set. And we can build this hierarchy of abstraction. We can use this hierarchy of abstraction to build the hierarchy of abstraction of mathematics. And all the way at the top of this abstraction, we have the grandparent class, which is the manifold class. Every data space is going to be an instance of a manifold. So this allows me to introduce, we're going to have a lot of diagrams. So let me just introduce the first connector of this diagram, which is the black arrow. When you see this black arrow between classes, it means is parent of. So for example, manifold is parent class of level set, which is parent class of hypersphere. Okay. And so that's the first connector, the black arrow, which is parent of. And then we introduce a second connector, which is attribute of. So an hypersphere is the level 0 of the level set defined by the function norm square equal to 1. So the hypersphere is easily defined as a level set by being embedded in a larger space that we call an embedding space. And so when we build this abstraction of classes that represent our data spaces with different geometric structures, we can give to these spaces attributes that are other spaces themselves. For example, if you look at the child class, it has its dimension attribute. So the hypersphere has a dimension, but it also has an embedding space dimension. Embedding space attribute, which would be typically the Euclidean space of dimension +1. And so the attributes that our classes have can be objects of different types. They can be either dim, which is an integer, but they can also be manifolds themselves. And they can also be Riemannian metrics, which are one of the first type of geometric structure that we will see. So we will build using this concept of object-oriented programming. We will build manifolds that are equipped with different mathematical structures. And that's what we're going to do now, actually use this concept of inheritance, attributes, and method to build differential geometry. Before I move forward, do you have questions at this point? All right, no question. So let's use the concept of object-oriented programming to build differential geometry.
No, wait, I actually do have a question. What does belong to?
What is the what, sorry?
What does belongs, the function belongs?
Oh, the function belongs, yeah, right, great question. So it's a method of each manifold. For example, when I have the sphere here, I can write I could write on the next line sphere.belongs, and I would give it one input point. And the sphere tells me whether that point belongs to itself. So sphere.belongs of point will return either true or false. It returns true if point is on the sphere. It returns false if point is not on the sphere.
Okay, so this is like standard like floating point issues, right? Like you just deal with it in the standard way of like errors and whatnot, I guess.
Floating point issue, yeah, we have a tolerance. Is that your question? Yeah.
Great, thanks.
Yeah, and by the way, Geomstats works in 3 backends, NumPy, PyTorch, and AutoGrad, and we test everything in Float 64, but you can also try to use it in Float 32. And you can play with the terms you want. Yeah, thank you. Great question. Okay, so we can use this general idea of classes with their attributes and methods to build, and the concept of inheritance, which is what represents mathematical abstraction, to build differential geometry. So we are going to start with embedded manifold. And here I show the manifold abstract class, which has a dimension, an optional private Riemannian metric. We'll go to this in a little bit. A belongs method. The manifold can tell whether a point belongs to itself. And an is tangent method. A manifold can tell if a vector is tangent to the manifold. There are 2 main ways of implementing manifolds in practice, which basically are 2 special cases of manifolds. Manifolds that are open sets within a larger manifold, so for a larger space. For example, an open set would be an open cone embedded in a Euclidean space, or another special case of an abstract manifold, which is a concrete implementation of an abstract manifold. That's other special case is the level set. So that's the example of the sphere. The sphere is the level set of the function square norm minus 1 equals 0, for example. So these are the 2 main ways we can implement practical manifolds in practice, and they follow the theorem that is on the screen. I'm just not adding its detail now. I'm going to show you examples that are child classes of both of these practical manifolds. So starting with an open set, we have the manifold of SPD matrices. SPD stands for symmetric positive definite matrices. And we see that there are many connectors here. But the first one that I want to point you to is this black arrow here. So that is saying that the manifold of all the symmetric positive definite matrices is a special case of an open set, which is itself a special case of a manifold. And we can indeed see that from the definition of the manifold of symmetric positive definite matrices, this equation refers to an open set. It's actually an open cone embedded in the vector space of symmetric matrices. So that's under the hood how the manifold of symmetric matrices is implemented. We can see that we have other manifolds available at the bottom of this slide. One of them in orange is the hypersphere we've been talking about. So first, the black arrow connector that is here connects the hypersphere to the level set. And so that is saying that the hypersphere is a special case of the level set manifold. That is how we implement it. And indeed, if we look at the formula, we see that the hypersphere is the level set of the function square norm. It's like or square norm minus 1, and the level is 0. So that's how the hypersphere is implemented in practice. We can also see that the manifold of SPD matrices has a dot here. This means it has an attribute, and its attribute is symmetric matrices. So this is saying that the SPD matrices manifold has an attribute that is its embedding space, and its embedding space is the space of symmetric matrices. And that's what we see in the first half of its mathematical equation, because sim n means the vector space of symmetric matrices. And similarly, the hypersphere has a gray dot here, which refers to its embedding space, and we can go all the way up, and its embedding space is a vector space. So just by using these connectors, we can have a view of what is implemented in the library, only talking about the manifold part. You have questions on this diagram? Okay, great. So that's the manifold, where we have an abstract concept of manifold, which is a space with some structure. We have two ways of implementing it, either as an open set or a level set. These two ways are still abstract at this point. And then we have all the concrete manifolds that are actual instances of open set or level sets. Now we are going to equip these manifolds. They represent our data spaces down the line. We're going to equip these manifolds with more mathematical structure, starting with a notion of connection or Riemannian metric. So I'm not going to go in the definition of what is a Riemannian metric. It's reminded on the screen, but basically you can think of it as a set of tools that allows you to compute distances or curvature on your data space, that is the manifold. And so now on the right of the screen, I'm going to show geometric tools, tools that we use to equip as an attribute any manifold with. So for example, the Riemannian metric, you can look at its methods. You can see it has a notion of norm, the norm of a tangent vector. It can compute dist, the distance between 2 points on the manifold. And the Ricci, sectional, and scalar, the three last are notions of curvatures. So we use the tool Riemannian metric, which is going to be a Python class in Geomstats, as a way to compute curvature of the different manifolds. So if we come back to the manifold that we had, and that we have actually implemented in the Python package, we see that they come with different types of metrics. So the manifold of SPD matrices comes free with 4 different ways of computing distances on it. And then the hypersphere comes with the traditional hypersphere metric that allows to compute distances between 2 points on the surface of the sphere by computing the length of the great circle linking the 2 points on the surface of the sphere. And that's our implementation of the first type of structure, that is the curvature of a manifold. Questions on this?
So a manifold has an attribute called metric. What is the metric attribute of SPD matrices in this case? Which is it, one of the 4 or like?
Oh yeah, that's a great question. So there is one default and you can change it.
I see.
And we just went through a major refactoring of the library as of 2 weeks ago. It didn't used to be like that, but now you have a default and you can change it. And I think that I forget which is the default, but now you have a Python function called equip with metric, and you can change the metric if you wish to.
Okay, sure, thanks.
Thank you. Okay, so that's the first type of geometric structure that you can equip your manifold with. It's the curvature. Now, in terms of symmetries, that is calling on notion of algebra and linear algebra, and specifically Lie groups. So we have a bunch of connectors that arise in that case. I'm not going to comment on everything, but I want to point out maybe one Lie group that you are aware of, which is the special orthogonal Lie group in green here. That's the group of rotations in 3D or in n dimension. So we can see how this special orthogonal group is implemented, where first we have this black arrow, which says that it's implemented as a level set. And it's true that the set of rotation is the set of matrices such that matrices R, such as R transpose R minus the identity equals 0. So it's indeed something that we can implement as a level set. It has gray dot connector that links it to general linear, because we implement the special orthogonal group as embedded in the general linear group of invertible matrices. And it has this square connector that links it to skew symmetric matrices, because the space of skew symmetric matrices is what we call the Lie algebra of the Lie group. So if the special orthogonal Lie group is the space of rotations, its Lie algebra is the space of infinitesimal rotations, and that's the space of skew-symmetric matrices. So that's for the special orthogonal, and you can see, again, it has 4 metrics that it comes with. These 4 metrics inherit from a structure called invariant metric. Invariant metric is a special case of Riemannian metric. It means if you have access to LD group, then there is a canonical way of building Riemannian metric on it. It's called an invariant metric. And we can create some metrics for the special orthogonal group using this recipe. Any question on that one? Okay, so that's symmetries, then it's using notion of linear algebra. And then we can also do some shape analysis. So the diagram is looking even worse, but it's the same idea. For example, you would have the space of closed discrete curves. So now you have a manifold where one point represents a closed discrete curve. And I've used that manifold, for example, to do research in cell shape analysis, so looking at the shapes of cells as they relate to cancer. And last but not least, we can implement information geometry. So information geometry is a field that is related to geometry and machine learning. Well, a manifold is a manifold where each point represents a probability distribution. And then you do statistics or machine learning on probability distribution. So in that sense, you have the manifold of gamma distribution in blue and all the way down to the normal distribution in turquoise. And on this type of manifolds, you can equip them with a special case of Riemannian metric that's called the Fisher-Rao information metrics. And so all of this is implemented in the library. Now, compared to other existing packages that have both geometry or like mathematical structures that can equip a data space and machine learning, our implementation of it is very abstract because everything follows the same framework, follows a common API. And so it means that just relying on these 2 lines, we can compute geodesic that are paths on a manifold between 2 points, just using the exact same 2 lines. So let me show you what I mean by this. Just with these 2 lines, I can compute a geodesic that is a path in the space of poses or in the space of rotations. Here, one rotation is illustrated as a 3D frame. And as we move on the space of rotation, we act on these 3D frames that moves as well, so that the geodesic you see on the screen is actually a trajectory in the space of rotations. Now, if I change the first line and I use another manifold, I use, for example, the manifold of closed curve, with the same 2 lines, I can compute a geodesic between 2 shapes of closed curves. And what you see on the screen is a blue curve deforming into a red curve. And the first one is an actual osteosarcoma cell that is deforming into another osteosarcoma cell, so bone cancer cell, while the second one is a more aggressive type of cancers. But what this shows is that you can compute a trajectory on the manifold of curved shapes and then visualizing that on the screen. And similarly, in information geometry, where one point represents a probability distribution, you can compute a trajectory between 2 points that are 2 probability distribution, and then visualize how that works. So I'm done with the implementation of differential geometry using a common interface. With the same 2 lines, you can compute trajectory on different manifolds. And that leads us to learning. By learning, I mean statistical learning, machine learning, deep learning, and more. And it's basically what is happening in the second step of this coverse perspective. So we want to do a machine learning algorithm that runs on the space that has some mathematical structure. First step is to create that space and have a lot of code within that space that makes that space aware of its mathematical structure. That was only the first step. The second step is to actually run a statistical learning algorithm, which led me to the architectural view of learning, where we're going to see that we have elementary operations, learning primitives, and then hierarchical organization. So lots of the machine learning or deep learning algorithm are built of these three things: elementary operation, machine learning primitives, and then organization of these primitives to build hierarchies, which gives the idea that if we can generalize all of these three aspects of learning, then we can have a more general theory of statistics, machine learning, and deep learning that will effectively take into account the structure that equip a data space. So let's start with the elementary operation. We can generalize elementary operations that exist on Euclidean spaces to our manifolds. So, for example, on a Euclidean space, the elements of your Euclidean space are points or vectors. These are the basic building blocks of everything that's happening in the machine learning algorithm. And we can easily generalize that to points on the manifold and tangent vectors on the manifold. And similarly, most of the algorithms that operate on Euclidean space use notions of straight line, distance, addition and subtractions. And these can be generalized on manifold as well. For example, a straight line is now called a geodesic. It's the straight line going from point blue to point orange on the Euclidean space at the top is now a geodesic going from point blue to point orange on the manifold at the bottom. Square distance becomes what we call the geodesic distance, and addition and subtraction become what we call exponential and logarithm map. So within Geomstat, we have translated the elementary operations that compute with basic building blocks of Euclidean spaces to basic operations, the equivalent operations that compute on manifold. So now that we have the basic element of language to compute on these manifolds, we can actually build machine learning algorithms. So in terms of the learning primitives, these are the machine learning algorithms that we have in Geomstats. So on the left, you have something called my manifold. For example, it's the sphere that you have instantiated. And on the right, you have different types of machine learning algorithms that are ready for you to use. And Geomstats uses scikit-learn API so that you can call this algorithm in the very same way that you will call scikit-learn algorithm. You have some base estimator type classes, some regression algorithm in green, some classification algorithm in orange, clustering in yellow, and transformation or dimension reduction in red. So this opens the door to geometric machine learning. And then lastly, you may want to be able to use both the elementary operations and the machine learning primitive to go towards deep learning with hierarchical design. And for this, Geomstat provides automatic differentiation backends. So you can use Geomstats in TensorFlow, PyTorch, AutoGrad, and JAX. Actually, I should mention that we have stopped the support for TensorFlow, so it might not be working as well as it used to because you're not testing that anymore. And adding JAX is still ongoing. But PyTorch and AutoGrad at least work. And so you can integrate the elementary operation from Geomstats and the machine learning primitive from Geomstat into more complex geometric and topological deep learning architecture, which leads me to a second package that we are working on these days, which is called Topo Model X for topological deep learning. And so that leads us to geometric and topological deep learning. So as a summary, with Geomstat, we have a blueprint for geometry in machine learning that relies on software design patterns of inheritance and object-oriented programming to implement the mathematical structures that can equip a manifold so as to have learning algorithms that leverage this mathematical structure. And the children of Geomstats is now TopoModel X, which is now deep learning focused. And so how to use this computational primitive to build next generation deep learning model. So yeah, I presented coding geometry for learning. In terms of future steps, we are trying to push the topological deep learning aspect and more specifically motivate the community to create an open source repository so that people that have contributed very important topological deep learning models can contribute their neural network. And if you're interested in this line of research, I would recommend that you participate in that effort and maybe consider participating in our next deep learning challenge at ICML. I'd like to thank the students and postdocs of our lab and also people funding this research. And thank you very much for your attention. I'll be happy to answer questions.
Thank you. Let us thank Nina for that great talk. Are there any questions?
I mean, I can keep asking.
Yeah, that's great.
So if you go back a few slides, is that picture with the classification of all the architectures? Yeah, this one. Is that from the TopoModel X paper, I assume, or something? Or?
It's close. So it's from a literature review of topological deep learning that we just submitted for publication. And it serves as the design document for TopoModel X. So basically, we reviewed all the neural network architectures available in topological deep learning and summarized them visually with this big table. And now our goal is to implement them all in a consistent API so that people can actually start doing appropriate benchmark and comparison of these models. So we have implemented a few of these neural networks in TopoModel X already, but we are organizing this challenge to ask others to contribute the remaining models so that together we build TopoModel X. And then the participants of the challenge will be invited to be co-authors of the TopoModel X publication.
Yeah, can you tell me like the name of that paper? I really like the picture.
Yeah, it's called Architecture of Topological Deep Learning.
Is it on the next?
Yes, it's here. The first one, Architecture of Topological Deep Learning. Yeah.
Picture of that. Okay. Yeah.
Thanks.
Okay. Do you have any like comparisons of like code between this package and like ones where you try to implement the same thing but in another package?
Yes, a little bit. So the scope is a bit different, but well, I'm not going to go through all the hundreds of slides. But we did compare ourselves in terms of speed to a package called PyRiemann, or Py for Python and Riemann for Riemannian geometry. That is a package specific for one manifold, which is the manifold of symmetric positive definite matrices. And we were comparable both in terms of accuracy and speed. Originally, I think when we compared ourselves, we were far slower. And then we found a bug and now we're comparable and maybe even better. But yeah, we didn't compare ourselves to all of these packages.
Oh yeah, I was looking more for like code shape or like just like see visually like which one does the code look nicer, you know?
I mean, you have some metrics of continuous integration, like percentage of code coverage. We're pretty good. I think we're, probably on average. Some of these packages were not tested at all. But among the ones that were tested, usually they are at 70 code coverage, more 70, 80 code coverage, and we are at 75, 80 code coverage. Okay. So yeah, at least on that part, we're pretty good.
You know, I saw this random paper from a couple of years ago on like Lee access neural Turing machines. Have you seen that one?
Sorry, did he access what?
Neural Turing machines?
No. But yeah, I'll be curious. What was it about?
So basically a neural Turing machine, except that the states are points on a Lie group.
Nice. Yeah, that's great. No, I hadn't seen this, but yeah, definitely very related.
Yeah, so it learns to create algorithms for like various counting things, but because so they implement it on like Euclidean space and on a sphere,
Nice.
where yeah, they're like geometric ways you can remember where you were a few states ago by moving in the right way.
Yeah, I mean, if they were using, for example, a Geomstat to do it on the Euclidean space and the sphere, then they could just replace the manifold with another one, and their code would work the same way. So we were trying to be plug and play in terms of the geometry.
Yep, that's nice. Yeah,
Yeah, thanks for the reference.
that's about what I have.
Thank you.
All right, let's thank Nina once more then.
Thank you.
Thank you. Let me stop the recording.